Hello and welcome to another NGen Math 8 lesson by eMath Instruction. My name is Kirk Weiler, and today we're going to be doing Unit 6, Lesson 4 on linear functions. Now, we've already talked about functions pretty extensively in the last 3 lessons. Like many things in math and in science, we divide functions up into various types, and one of the most important types is what's known as linear functions. So let's get into it right away and talk about what a linear function are. What a linear function is. Now, there are many important types of functions. Linear functions are simply those whose graphs form straight lines. In fact, you can actually see the word line in the word linear, right? There it is, L-I-N-E, linear. Well, okay, it's linear. But anyway, any function whose graph just forms a straight line, input, output pairs all lie on a straight line, is what's called a linear function. And these are just some of the most important functions out there, primarily because they're very simple, right? Their equations are simple, their behavior is simple, all of that. And what we want to do in exercise 1 is we want to look at probably the most important thing concerning linear functions. So let me bring exercise 1 up to the top, and let's take a look at it. Consider the linear function y equals 3/2 times x plus 2. Answer the following questions. Letter A, find the average rate of change for each of the following intervals. Show your work. Letter B, what important characteristic of the line do both your answers from A equal? All right, so why don't we do the easy one together, the first one, then we'll have you do the more challenging one on your own. Now remember, average rate of change is the change in the function's values divided by the change in the input values. Now, unfortunately, we're given the 2 input values in both cases, but we have to calculate the output values before we find the change in the output. So let's do that together in letter A. All right, so when x is equal to 0 in this function, y is equal to 3/2 times 0 plus 2. Of course, anything times 0 is 0, and 0 plus 2 is 2. All right, so when x is equal to 6, y is going to be a little bit harder to calculate. 3/2 times 6 plus 2, right? That's going to be 9 plus 2, and that's going to be 11. So now my average rate of change, got to squeeze it in here, my change in y divided by change in x is going to be 11 minus 2 divided by 6 minus 0. That's going to be 9 divided by 6. And I can simplify that by dividing numerator and denominator by 3. And I'll get an average rate of change of 3/2. All right. Simple enough, okay? I'd like you to do exactly the same thing, but now having inputs that go from -4 to 4. Pause the video now and take a few minutes to do this. All right, let's do it. We got to figure out what the y values are for these 2 x values. That's going to become our beginning step. So for x equals -4, y is equal to 3/2 times -4 plus 2. Got to be careful here. That's going to be -6 plus 2, and that gives me an output of -4. So for an input of -4, we have an output of -4. We won't get so lucky when our input is +4. When our input is +4, right, we'll get 6 plus 2, and we'll get 8. Now this is a little bit more tricky, right? We got to watch out because of our negatives and our positives, right? Our change in y is going to be 8 minus -4, and our change in x will be 4 minus -4. That's going to give us 12 in the numerator, 8 in the denominator. We can divide both of those by 4, and we'll get 3/2. Now, for most functions, in fact, for all functions that are not linear, the average rate of change over one interval doesn't tend to be the average rate of change over another interval. And yet these 2 average rates of change were the same for both the interval that goes from x equals 0 to x equals 6 and x equals -4 to x equals +4. And that brings us to letter B. So let's revisit that just for a moment. What important characteristic of the line do both your answers from A equal? So both of them, they're both equal to 3/2. I mean, you can see it right here, right? Y equals 3/2 times x plus 2. What is that 3/2? Pause the video now and write down what important characteristics of the line the average rate of change is equal to. Well, it's equal to the slope, right? The slope of the line. In fact, the slope of the line equals the rate of change. And what really makes a linear function is that that average rate of change doesn't change. It doesn't matter what interval you look at it on, the change in y divided by the change in x for a linear function, no matter what the x values would have been. I could choose x equals negative 100 as my first x value and x equals 5 as my second x value. And if I went through all of this and I reduced my fraction at the end, it would equal 3/2. The slope of a line is its rate of change. It's how fast the output, the y value, is changing compared to the x value. That's what makes a linear function linear, right? The defining characteristic of a linear function. Linear functions have constant rates of change equal to their slopes. Any 2 points on a linear function will allow you to calculate the rate of change. And granted, it's just that one rate of change. We'll look at some non-linear functions eventually, functions whose rates of change do depend on the input-output pairs. But for linear functions, it really doesn't. So let's take a look at a good example of a linear function in exercise number 2. A balloon is let go at a height of 4 feet above the ground and rises at a constant rate of 2 feet per second. All right, letter A. Fill in the table below for the height of the balloon. Great. All right, so in other words, we're tracking the height of this balloon as a function of the time since it let go. I'd like you to try to fill in this table given that when we let it go, at t equals 0 seconds, it's 4 feet above the ground, and for every second that passes, right, the height changes, gets larger by 2 feet. All right, so pause the video now and go ahead and fill in the table. Well, at 0 seconds, it's 4 feet above the ground. Now the whole point about this rate, right, and of course you can always spot a rate in a problem with the word per, right, is that for every second that passes, the height is now going to get higher by 2 feet. So at 1 second, right, when we raise that height of 4 up by 2, it's going to go to 6 feet, and then 8 feet, 10 feet, 12 feet, and 14 feet. All right. Letter B asks us to graph the data from the table and connect with a line. Why don't we do this together? This isn't too tough, right? It's just graphing coordinate pairs. I want 0, 4, right there. 1, 6, 2, 8, 3, 10, 4, 12, and 5, 14, right? And it says connect them with a straight line. Maybe I'll extend that line all the way out. Of course, I hope you do it with a ruler. I just kind of did it freehand to save a little bit of time. Now, keep in mind, right, from our unit on just sort of equations of lines, right, when we have the equation of a line, there's two things that are important. There's the slope, or the rate at which y is changing compared to x, and there's the y-intercept. So what are those for this particular problem? Pause the video now and see if you can put the slope and the y-intercept in. Well, the slope is always the rate, right? It's always how fast per blank. There's your slope, 2 feet per second. I'm just going to write it, though, as the number 2. Now, I know that in the last unit we were very used to seeing slopes as fractions. I mean, even in that first problem, we had a slope of 3/2, right? If you really wanted to, you could write this slope as 2/1, right? But you don't have to. And in fact, that would look a little bit awkward. Now, the y-intercept is, of course, where the line crosses the y-axis, or better yet, for a linear function, it's where the function begins, right? The function begins at 4 feet above the ground. That's your y-intercept, is 4, okay? Now, we can do some things with the slope and the y-intercept. And in fact, we're just going to keep on working on exercise number 3. Let's take a look. In the last exercise, our input variable was time, t, and our output variable was height, h. Given your answers to exercise 2c, write the equation of the line a in y equals mx plus b form and b in h equals mt plus b form. So here's what I'm getting at with this exercise, right? In the last unit on lines, right, we always wrote equations of lines as, y equals 3/2 times x plus 2. That was our first exercise, right? Or y equals negative 5x plus 7. It was always y's and x's, okay? Where, remember, m is the slope and b is the y-intercept. So if I wanted to write the equation of the line I had in exercise number 2 in terms of y and x, I would simply have it as y equals 2 times x plus 4, right? And if you grabbed any one of these particular values of input, right, these input values, and you threw them into this equation, it would give you these as the output values. But notice, right, really the two variables here aren't x and y, they're t and h. And if at all possible, you always want to write the equation of a function in terms of variables that have some kind of meaning to them. H for height, t for time. So in letter B, where I ask you to write the equation in h equals mt plus b form, all I'm saying is this is a better way of writing it than this. Right? Because this really doesn't have any kind of real meaning to us, whereas this I can say, oh, the height of the ball is 2 times the time plus another 4, right? I start 4 feet above, and for every second that passes, I get 2 additional feet of rise. It's kind of cool. Now, what's really nice about linear functions, the reason that they are so useful, is that they model a lot of problems exactly like this. And what I mean by that is the equations of all linear functions can be summarized by y equals the rate times x plus some initial value. So in the last problem, that initial value was 4 feet above the ground when the thing started to rise, and it was rising then at a rate of 2 feet per second. So our equation, in terms of y and x, was y equals 2x plus 4. Now the only thing that's tricky about this at all is that occasionally the rate can be negative. And we know that the rate will be negative when the output is decreasing. When the output is going down, then that rate will have to be a negative number. Let's take a look at exercise 4 and get some practice writing the equations of linear functions given real-world scenarios. Let's take a look. For each of the following scenarios, identify a rate and an initial value given and write the linear equation that models the scenario. All right, and we're going to do all of these in terms of y's and x's, okay? So no h's and t's, but y's and x's. So let's take a look at letter A. Oh, actually, maybe we're not going to do it in terms of y's and x's. I apologize. Letter A, Lizzie has $50 in her bank account. She decides to save an additional $15 per week of her allowance. If she doesn't spend any more money, write a linear function for the amount of money she has saved, A, as a function of the number of weeks, W, she has been saving. All right, so let's back out of this for a second. For a linear function, you really need two things. Sort of something you're starting with, some initial amount, like in that first, not the first exercise, but exercise number 2, right? The ball started at a height of 4 feet above the ground, and that's your y-intercept. And then you've got to have a rate that thing is changing per something. And it's very often very easy to spot the rate, right? Here's a rate. Right? $15 per week. And that's going to be the slope, right? Now, it's pretty obvious that they also gave us, right, an initial amount. Lizzie started with $50 in her account. So the slope, right, is going to be 15. The initial value is going to be 50, the y-intercept. Now, before we move on, let's talk about why the slope is positive and not negative, right? The plain fact is Lizzie is putting or saving an additional $15 per week. So the amount of money that she saved is going to go up as time goes up. The amount of money is going to increase, and therefore the slope is positive. If we had said that Lizzie takes out $15 per week, then of course the amount of money that she would have saved would be going down, and our slope would be a negative 15. All right, it's very important. Context will tell you whether the slope is positive or negative. In this case, it's positive. So at the end of the day, right, I want the amount saved as a function of the number of weeks. That means the A is sort of my Y, and the W is my X. So the amount that she saved is 15 times the number of weeks plus that initial $50. All right, Y equals slope times X plus Y-intercept, or in this case, the amount of money is equal to $15 per week times how many weeks have passed plus the initial $50 that she had saved. All right, let's take a look at letter B. An elevator begins 120 feet above the ground. Its height decreases at a rate of 4 feet per second. So, the elevator's going down. Write a linear function for the height h of the elevator above the ground floor as a function of the time t in seconds that it has been moving downward. All right, I'd like you to pause the video now and try this problem. There is something a little bit tricky about it, but see if you can figure that out. All right, well, there's nothing tricky about the y-intercept, okay? That's always where we begin. In letter A, we began with $50 in the savings account. In this particular problem, we begin 120 feet above the ground. That's simple. But here was the tricky part. The height decreases at a rate of 4 feet per second. In other words, we're going down on this elevator, and the y variable, or in this case, h, is going to decrease as time increases, so the rate must be negative. The rate is -4, right? It's not +4. If you had +4, what that would mean is that you're going to get on at 120 feet above the ground and you're going to go up at 4 feet per second. But it's very clear that the height is decreasing here, so the rate must be negative. Literally, decreases means a negative rate. That is so very important. So now the equation is pretty easy. The height is going to be -4 times the amount of time plus that initial value of 120. That's it. All right, let's take a look at one more. That's as high as it's going to get. Actually, let me bring it up a little bit farther. There we go. Let's take a look. A container weighs 6.5 pounds and is filled with bricks that weigh 1.5 pounds per brick. Write a linear function for the total weight of the container, W, and a function of the number of bricks, as a function of the number of bricks that have been placed in it. All right? So yet again, pause the video and see if you can write this equation down. All right, great. Here we go. So, what do we have? Well, we know a container weighs 6.5 pounds. So without any bricks in there whatsoever, we've got some kind of container that weighs 6.5 pounds. That's our y-intercept. It's our initial amount. Now, is the weight increasing or decreasing as we put bricks in, right? 1.5 pounds per brick, we're putting bricks in, right? So the weight is going up, right? Every brick we put in, the weight goes up by 1.5 pounds per brick. It would be pretty tricky to put bricks in and have the weight go down. Don't get me wrong. You could easily say something like, oh, we had a container with bricks in it that originally weighed 22 pounds. We started taking bricks out, which weighed 1.5 pounds per brick, write an equation, for, the weight, depending on how many bricks we've taken out, in which case it would be going down. But we're putting bricks in here, so therefore the rate, the slope, is going to be positive. 1.5 And therefore, my linear function, the weight is going to be 1.5 times the number of bricks I've put in, plus that initial weight of the container. And that's it, right? So let's wrap this up, right? Linear functions are critically important because of what we just were looking at. They model a lot of real-world scenarios where you start with some kind of initial value, and then that value either goes up at a constant rate or goes down at a constant rate. And when you have that, then using y equals mx plus b, where m is the rate and b is that starting amount, is an extremely easy thing to do and also extremely useful if you then need to use that linear equation, that linear function, for what are known as predictive purposes. Predicting, well, how much is it going to weigh after I've put in 55 bricks? Or, where is the elevator going to be after its height has decreased by 4 seconds? All right, these types of linear functions can help us model a lot of things in the real world and answer a lot of questions that we might have. For now, I just want to thank you for joining me for another NGen Math 8 lesson by eMath Instruction. My name is Kirk Weiler, and until next time, keep thinking and keep solving problems.